Welcome to Mrs. Z's Chemistry. In this video, we will learn about precipitation reactions. A precipitation reaction is one in which a dissolved substance react together to form a solid product. So imagine you have two beakers and they're each filled with a dissolved ionic compound. So they are both clear, colorless solutions sitting in the beakers. And then you mix them together and sometimes a solid is formed from the products. And this is what is called the precipitate. What's happening is that an ion that's dissolved and aqueous in one of the beakers is more attracted to another ion in the other beaker than it is to water. So these two particles then stick together and they form the solid. Usually they sink to the bottom, and this is what is called the precipitate. Then the other ions that are left in the beaker are still aqueous and floating around in solution. And this is a double replacement reaction. We have to use solubility rules to determine which compound on the product side will be the solid precipitate, or if we have one at all. So if a compound is determined to be soluble by the rules that I will show you in a moment, then that means it can be dissolved and it's aqueous. And the two ions will float around in solution and they don't form a solid product. But if the compound is considered to be insoluble, then that means it can't be dissolved and it is a solid product. So here are the rules. They are listed by anion, by the negative part in the ionic compound. So if the anion is in the soluble compound list, one of these here, then we follow these rules. That means it is generally soluble. If one of the positive compounds, or the positive part of the compound is listed in this exception, then that means it's not soluble and it is in fact insoluble. So let's look at this. If the anion we're looking at in the compound is either nitrate, the NO3, or perchlorate, ClO4-, or acetate, CH3COO-, then all of these are soluble no matter what positive compound that it is making a compound with, because there are no exceptions. So it's always soluble, always aqueous. If the anion in the compound we're looking at is either chlorine, bromine, or iodine, then most of the time this is a soluble compound. But if the positive cation that it is making a compound with is either silver, mercury, or lead, then this is insoluble. So that would mean either silver chloride, it would be solid, or if you've got silver bromide, that would also be solid, or silver iodide, that would be solid, or if you had lead chloride, that would be solid, or if you had lead bromide or lead iodide, and so forth. Same thing with the mercury. All of those would be solid. However, if you had something else with the chlorine, like sodium chloride, that would be aqueous, because sodium, Na, is not one of our exceptions. There are some anions that are usually insoluble. So if you had any of the polyatomic ions, carbonate, phosphate, or chromate in the compound, if that was the negative part of the compound, then usually it's an insoluble compound. However, the exceptions include ammonium, NH4+, and alkali metals. Alkali metals are just the metals in the first column on the periodic table. So for example, if you had carbonate, the CO3 2-, and it was making a compound with ammonium, not with the positive charge, we're going to make a neutral compound here, then this right here is an exception to the insoluble rule, and this is in fact aqueous or soluble. But if carbonate was forming a compound with something that's not on this exception list, like say calcium is in the second column on the periodic table, so this is insoluble, and we would write it as solid. So then we have sulfide ion and the hydroxide ion. These two right here, these are usually insoluble, and our exceptions include the ammonium ion, as well as the alkali metals and calcium, strontium, and barium. So again, if the compound is insoluble, then it is solid, and we write a little S after it in the chemical reaction. And if the compound is soluble, then that means it is aqueous, and we write an AQ after it in the chemical reaction. Whenever you have H2O in the chemical reaction. It is either solid, liquid, or gas. It is not aqueous, because aqueous means dissolved in water, and H2O cannot be dissolved in H2O. That would not make sense. So let's try some practice here. Is it soluble or not? Looking at the rules, let's go to the periodic table. The solubility rules are at the bottom back of the periodic table here. So we were looking at silver nitrate from that list of practice. So we look at the negative part. Nitrate, NO3, is the negative part. We're finding nitrate on the soluble compound list, and there are no exceptions, meaning silver is not an exception to this, and this, in fact, is aqueous. So we can write on our slides here that we have an aqueous compound. Let's look at lead chloride and potassium sulfate as well. So lead chloride, chlorine is the negative part of the compound, and we find that here in the soluble compound list. That means most of the time chlorides, compounds with chlorine, are soluble. However, let's look at the exception. The exceptions for chlorine include these three elements. Lead is one of the exceptions. So that means that we have a solid compound here. Lead chloride is not soluble, it is insoluble. The other one we were going to look at is K2SO4. Sulfate is also on the soluble compound list here. And potassium, the K, is not one of these exceptions. So that means this follows the general rule of being soluble and aqueous. Following the rules on your periodic table, go ahead and see if you can figure out whether each of these compounds are either solid or aqueous. And here are the answers. So now let's take this solubility practice and turn it into a precipitation reaction. When sodium carbonate and calcium nitrate are mixed, is there a precipitate? So this is asking, when these two are mixed and we predict our products, are one of the products a solid or not? If there is a solid on the product side, then that means yes, this is a precipitate reaction. But if there is not a solid, if both of the products are aqueous, then that means no, this is not a precipitation reaction, there's no precipitate, and that actually means no reaction happened. So let's go ahead and try this. We have sodium carbonate and we have calcium nitrate. We need to predict our products. Sodium is a +1 charge, carbonate is a -2. Calcium is a 2+, and nitrate is a -1. So we're going to take this positive from the first compound, sodium, and the negative from the second compound, nitrate. We write sodium nitrate. Sodium is still a +1, nitrate is still a -1. We have to create neutral products on the right-hand side. So we just write this as NaNO3. I know that there was a subscript sodium on sodium here and a subscript on the nitrate, but that will be resolved when we balance this reaction. You do not carry over subscripts unless they are part of the polyatomic ion, like the 3 here. The 3 goes with the oxygen, and those 3 oxygens always stay with the nitrate, or the nitrogen. All right, now we're going to take the positive calcium and the negative carbonate. Calcium has a 2+ charge, carbonate a -2, so this makes a neutral compound, just one of each, 1 calcium and 1 carbonate. That 3 on the oxygen is part of the polyatomic ion, and it does not move. All right, now we can balance the chemical reaction. So we have 2 sodiums and 2 nitrates on the left-hand side, so let's put a 2 coefficient on the right-hand side. So now we have 2 sodiums on both sides, 2 nitrates on both sides, 1 calcium on both sides, and 1 carbonate on both sides. Now we got to look at our solubility rules. According to the solubility rules, sodium nitrate is aqueous. Nitrate is always aqueous. It's always soluble with no exceptions. Carbonate, let's look at our periodic table here. Carbonate is actually on the insoluble list, which means most of the time carbonate compounds with carbonate, are insoluble and solid. Calcium is not one of these exceptions because calcium is not an alkali metal. Alkali metals are just the first column and calcium is in the second column. Therefore, this is not an exception to the rule, and calcium carbonate is solid. So the answer is yes. There is a precipitate, and calcium carbonate is the precipitate. So this is a precipitation reaction. Let's try another one. When sodium chloride and calcium nitrate are mixed, is there a precipitate? If so, write a balanced chemical reaction. So we're going to write out sodium chloride plus calcium nitrate. Sodium is a positive charge, chlorine has a negative charge. Calcium has a 2+ charge, nitrate only a -1. We're going to take, I'm going to change colors here, the positive from the first compound, the negative from the second compound, and we write it out, NaNO3. Let's relook at our charges. Sodium is a +1, nitrate is a -1. So we just need one of each here, one sodium and one nitrate. Don't worry about the fact that we had 2 nitrates on the left-hand side. We'll resolve that when we balance the whole reaction. Now we take the positive from the second compound and the negative from the first compound, and we have calcium chloride. Calcium is a 2+ charge, chlorine is a -1. So this is not a neutral compound the way it is written here. We need 2 chlorines in order to make a neutral compound. 2 -1 chlorines neutralizes the 1 + 2 calcium. I know there was not a subscript 2 on the left-hand side. We did not just spontaneously create an extra chlorine atom. We're going to take care of this when we balance it, which is what we're going to do right now. So we have 2 nitrates on this side. So let's go ahead and put a 2 coefficient out in front. So now we have 2 sodiums and 2 nitrates here on the right-hand side. So that balanced the nitrates, but we have unbalanced our sodium. Since we have 2 sodiums here, let's put a 2 coefficient out in front of the sodium chloride on the left-hand side. Now we have 2 sodiums on both sides, and now we also have 2 chlorines on both sides. 2 chlorine on the left hand there, and then the 2 chlorines here. So now this is a balanced chemical reaction. All right, looking at our solubility rules, all of these compounds are aqueous. So let's look and see what happens here. Let me label. When a compound is aqueous, that means it is dissolved in water. That means that the sodium and the chlorine are not stuck together. They are separated and floating around in solution all over the place, separate away from each other. So is the calcium nitrate. Because it is aqueous, the calcium and the nitrates are not stuck together. They're floating around independent of each other in the solution, in the water. Once we mix these two products, you can imagine we've got this beaker right here with lots of calciums and nitrates in that 1:2 ratio, and we've got this beaker here with the sodium chloride, the sodium ions and the chloride ions. Then we mix those beakers together, and we have one big beaker full of sodium nitrate and calcium chloride. Well, since both of these are aqueous, that means we have sodium nitrate is floating around in solution, and then your calcium and your chlorines are all floating around in solution. So let's look at this. We have 2 sodium ions and 2 chloride ions. We also have 1 calcium ion and 2 nitrate ions. On the product side, we still have 2 sodium ions and 2 nitrate ions. We have our 1 calcium ion, and we have our 2 chloride ions. So this is what happens. Our ionic equation looks like this right here. We have split up all the aqueous compounds. When we're writing out ionic equations or net ionic equations, something I will explain in a moment, we need to split up all of the aqueous compounds. Because this reaction has 4 aqueous compounds, that means no reaction happened. All of the ions, the sodium ion, chloride ion, calcium ion, and nitrate ion, they were aqueous and floating around in solution before we mixed the 2 beakers and also after we mixed the 2 beakers. Let's try another example. Potassium chloride and lead nitrate are mixed. Is there a precipitate? Pause and see if you can predict the products, balance the equation, and also predict the solubility, whether or not the products are solid or aqueous. So here we have our aqueous potassium chloride. We have our aqueous lead nitrate. The products are potassium nitrate and lead chloride. The first 2 reactants are aqueous. The potassium nitrate is aqueous, but the lead chloride is solid. So let's look and see what this is. Because potassium chloride is aqueous, we need to split up the ions. They are not touching each other in solution. They're floating around all over the place in their beaker. So we have 2 potassium ions and we have 2 chloride ions. Then in the second beaker we have lead nitrate, which is also aqueous. So the nitrates and the leads are not stuck together. They are separated and floating around in solution. That's on the reactant side. Remember, imagine we've got two beakers here, one beaker for the lead nitrate, a beaker for the potassium chloride. Then we mix them together, and what ends up happening is that the potassium is still aqueous and the nitrate is still aqueous. So they're all split up in solution. But the chlorine and the lead are stuck together. They are more attracted to each other than they are to the water molecules. So this lead chloride is a solid, and we don't split them up into solution. We keep them stuck together and touching each other, so to speak, if you were to draw the molecules like this and the particles. So we still have two potassium ions and two nitrate ions, but we have a lead chloride, and you write this all together as one chemical compound and put the little S solid after. Now the next step here is to cancel the spectator ions. That means we're going to cancel the ions that are the same on both sides of the equation, the ions that did not change. Potassium is aqueous on the reactant side, and it's aqueous on the product side. So we get to cancel the potassium ions. The chlorine, though, the chloride ions were aqueous on the reactant side, and they're solid on the product side. And so we can't cancel that because it changed. It went from aqueous to solid. The lead as well went from aqueous to solid, so we cannot cancel the lead either. It changed. It participated in the chemical reaction. The nitrate, though, is aqueous on the reactant side and aqueous on the product side, and so it actually did change. Now we rewrite what we have left, the things that we did not cancel. This is what we call the net ionic equation. Here is it all typed out. We've got our ionic equation and the net ionic equation. After we cancel the things out, what's left is considered the net ionic equation. You must include charges on the reactant side. You can write them in either order, lead ion or chloride ion first. But then when it's a compound, the cation, the positive lead, must always go first. All of the other ions, the ones that we canceled, the potassium and the nitrate, these are called the spectator ions. I like to call them the fans in the stands. They're just watching the show being the reaction, which is, in this case, the lead chloride, going from aqueous substances to solid substances.